So the recording had some problems, so I re-recorded it in places. So if it sounds odd, it's because of that.
All right, let's get started. So, um, last time the recording didn't like pick up the first half, so I kind of have to re-record that. But if ever when you watch these, um, you know. So, yeah. All right, so today we are going to talk about startup and what EQ will be 2 weeks from today. Okay. Next week, I don't know, maybe the AQI goes a little bit into next week. I don't know. Next week we'll talk about COVID, and then stratospheric ozone depletion. Okay, we'll have a check on the air quality. Um, right? Start doing it. Homework number 2 is due today. Homework number 3 is due next Tuesday. Okay, here those are. So the number 2 is on mechanisms a lot, and OH reaction. Number 3 is on ozone and aerosols. Okay. Here's the air quality lab info that's due on the 21st. The midterm on 3/12. Okay, so first, there are things you should know for part 1. Okay, these tend to be more conceptual, right? And so, right, 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 or atmospheric structure. Part 2 is via Canvas. It's also 40 points. You have a 2-hour time limit. You can use any notes or slides possible, or you could rewatch my videos, but you don't have enough time for that. Okay. You must work alone. Okay? That is due. I'll give you a 3-day time window. So from Tuesday. You notice on here, so for that atmosphere, part 1, you need to know about structure, profile of temperature and pressure, weather versus climate. For midterm part 2, you need to know about the calculations, how to do that. Okay. Or, have your notes ready to do that. Okay. I think it's fairly straightforward, but if you have any questions, let me know. Okay. Oh, notice that on the back page in bold for pollutant chemistry, part 1, you do need to know the production scheme from VOCs, OH, NOx, and UV, right? So know those reactions. Okay. Yeah. All right. Any questions? Okay. I didn't post it yet. I will post it soon. Yeah. Journal Club. Oh, I forgot to update this. But I think everyone said it was okay, except I haven't heard from Yashvi if it's okay or if she wants to switch her dates or whatever. Anyone have any issues? Okay. The next one is March 28th, so we still have some time, obviously. All right, last time we
All right, so last time we didn't add anything to the Hall of Fame. This time we were talking about if there's anything to add. One of the things that was added was black carbon, which is also known as soot. Black carbon or soot comes from combustion. primarily from incomplete combustion. So from wildfires, etc., you get a lot of this soot. It's really important for climate change reasons. It is also important for health reasons, but we think about it mainly for climate change. The second type of aerosol we're going to add is sulfate aerosol. Sulfate aerosol comes from SO2, which SO2 gets emitted from fossil fuels and power plants, and then it gets converted into sulfate, which is an aerosol. And so, unlike black carbon, which absorbs light, sulfate actually scatters light. Another aerosol that was added were PAHs, or polyaromatic hydrocarbons. Polyaromatic hydrocarbons are organic aerosols that come a lot from combustion. They are important for health reasons. They are mutagens.
Sulfate from SO2. Oh.
So last time we finished up talking about air pollution. So we talked about the EPA criteria pollutants. You should know all 6 of these. And ozone and aerosols, those are the primary ones. We talked about sulfur dioxide, SO2. It's highest in the eastern US because of the most coal usage there. There have been reductions since 2000 because of cleaner coal. Then we talked about aerosols. We talked about 3 reasons why we care about aerosols. And we talked about aerosol composition. So we have inorganics and organics. Here's a plot of aerosol composition throughout the world.
Applications, you have different things, right? So in bioaerosol be the predominant source. Over the ocean, sea salts there, primary source. North America, Europe, China, that brownish, that it depends on the species, right? There's no black box. There's no one thing that can measure everything. Okay. It depends on the species. And one of the big things is the reactivity, how long they stay in the atmosphere. If it's long-lived, it's kind of easy, right? If you can get something and you can trap it, you can measure it a day later, a month later, right? If it's short-lived, you can't really collect it, right? If something lasts in the air, you can't take it and measure it a week later. And we can talk about what's called real-time versus delayed measurements, right away or measure it later. And then in situ versus remote sensing, where in situ means at a location, right? So if I have a sensor that measures the aerosol in this room, right, that would be in situ. A remote sensor would be something that...
So a remote sensor is something that measures something that it's not in contact, like satellites.
All right, so we're going to look at gases, aerosols, and then remote sensing. So let's start with gases. We can talk about long-lived species like hydrocarbons or CO or CO2, or more short-lived species, right? The radicals and ozone. The first technique is GC. Okay. You've all used GC, right? You can inject something onto a column, you run it through that column, right? You heat it up, and you look at the emission coming out of it, okay? The nice thing about GC is you can separate different compounds, okay? So GC is useful for very long-lived. So for instance, my old, when I was in grad school, see this silver canister? You can kind of make it out. It's against the lamppost, but there's a valve on the top. Basically, we took.
So the canister was evacuated, so it had a vacuum. You put a valve on the top, and so it's closed off. You can take that canister wherever you want in the world. This photo is in Chile, and basically you open it up. And what happens is, because there's a vacuum, gas from outside goes in. You can close that off, and then you can take that canister, ship it back to wherever your lab is, and you can analyze it. This is good because you can measure hundreds of compounds as long as they're going to be long-lived in that canister. But it's delayed measurement, so you don't know until you get it later. And it also has a low sample frequency. You can't take samples that fast, right? The fastest you could do it probably a sample every 1 minute, but even that's likely not happening. Once you get it back to the lab, you can go ahead and you can use a variety of techniques, typically gas chromatography. And so on the right, these are some hydrocarbons that could be measured with the technique. So you inject it in the sample injector, you have gas flow going through, and it goes through a column to separate.
Who's in instrumental analysis? Who's taken instrumental analysis? You did, right? Yeah, okay. All right, so, and I'll be taking quant, right? Okay. What is a good detector for measuring hydrocarbons? They have carbon and hydrogen. A good detector, right? So in GC, you inject it in there, it goes through a column, and then you have a detector, right? And that detector gives you that, right? But it's not magic, right? It's not, the GC is not like a bouncer, right, with one of those clickers, right? How does it know that a hydrocarbon passes by? Tell me something about hydrocarbons. They're volatile. You were about to say something else, I think, right? All right, hydrocarbons like propane, methane, octane. Tell me something about those. Methane, propane, octane, butane. What have you ever, your cousin, not a chemist, they've heard of butane, right? Why have they heard of butane? It's what? It burns, right? It's a lighter. Propane, that's a propane tank, right? How about octane? That's gasoline. Methane, that's your stove, right? Hydrocarbons burns them, right? So the best detector for hydrocarbons is called a flame ionization detector. You should know this. You should know this for the future. Because if you're going to be a chemist, right, and get a job somewhere, GCFID, that's, so you take the compound flows through there, and you have a flame, and it flame ionizes it, and then it detects it. Okay, so FID, great for hydrocarbons.
But what if you want to measure something that doesn't burn, so it's not a hydrocarbon? Well, the best way to do that is with what's called a mass spectrometer, or an MS. This is what you have when you say a GCMS or an LCMS. And so what a mass spectrometer does is it takes your sample, it ionizes it, and then it separates the different ions based on their mass to charge ratio. That's a lot of times called the M to Z ratio, M over Z.
Right? Usually how it separates, right, is either a quadrupole or something else, right? So you basically take it in there, right? And how long it takes, well, in a quadrupole, you have those forked poles and you change the voltage, and once of a certain mass to charge ratio makes it to the detector, right? You can also do something similar with a reflectance, right? So it goes down and it comes back, right? So a mass spectrometer, right, forms ions.
And then those ions enter the separation, which separates out the different mass to charge, and then you have a detector. Now what you can do is you can put a MS after a GC. So you have GC that does separation of the different molecules, and then you can have those molecules, those compounds come into it and be ionized and then detect.
Right? If you have really short-lived species, right? Because the GC, that takes a while, it's going to react away. But if you have something where it just goes straight in the instrument, you can measure it right away.
So there are two types of mass spec. Okay, there is, and I asked students what they are. There are two types, and the primary one, the one you probably use the most in lab, is what's called electron impact or electron impact mass spectrometry. So this is how you form an ion in mass spec. So what you have is your analyte M, so your compound, it comes into an area where you have a voltage across, and usually a filament, and that filament produces electrons, and so those electrons go from the filament towards the other side, and the analyte goes through it, and basically the analyte gets hit with all these electrons, and what happens is you get fragmentation. This is what we call hard ionization. It produces a lot of different fragments, and because of this, you can't really determine what's called the parent ion, what it started out at, that M plus, because it just breaks apart.
Okay, this is just one example. This is N9-acetyl oxy nonanol. I'm not an organic chemist. I'm always hard with putting these all together, you know. But that compound there, it has a molecular mass of 200. Okay, this is its electron impact mass spectra, right? Notice you get all these fragments, none are at 200, okay? Or 199, usually you just think, right? Why? Because each one of these is a different fraction, okay? Let me think. CHO, O is 16, right? So this would be 29 right here, right? So then if you add on another 12, that will get you to 41. Okay, so this first one, which would be a CH, H, C double bond O, H, right? This is that 43, right? Then you add on a carbon, that's the 55.
So this is an example of hard ionization with with electron impact. Notice that the parent ion, that 9-acetyl oxy nonanol, which has a molecular weight of 200 grams per mole, we don't see 200 grams per mole on there. Why? Because it all got broken apart into these different fragments. That's why we call it a hard ionization. The second type of mass spectrometry, or at least of the two major types, is called chemical ionization mass spec, or CIMS. And This one, you form an ion, not by taking the molecule and hitting it with electrons. Here, you form a previous ion. So here, you're taking H2O and you're forming H3O plus, and you're having that H3O plus hit your analyte here being that R. And what happens is some of those H plus transfer over from the H3O plus to that R, that molecule, and that you get RH plus, and that's your ion. And so notice you form that ion, actually that parent ion plus one, and then it goes through a quadrupole, and then it goes to the detector. And so this is much softer. This has less ionization occurring, less fragmentation occurring.
You all have done electron impact mass spec. That's pretty much, we learned, when I was taking, whatever class, quant or whatever, I learned about these two things, right? I've only ever used electron impact, right? Chemical ionization is more rare, right? Or is, more rare. But remember, this one is what I saw for 9-acetyloxy nonenal, mass spec of 200 or molar mass of 200 for EIMS. For chemical ionization mass spec, right, you get this. So a lot less fragments. And notice here is your parent ion. It's actually not your parent ion. It's the parent plus one. What gives it that extra one mass? What element? What element has a mass of one? Hydrogen, right? In this case, it has gained a hydrogen. Okay. So a lot cleaner, I think I showed on the next one, right? So you have electron impact and you have SIMS, right? The SIMS is a lot easier to figure out what it is. Okay. So why would you even do the electron impact? Cheaper and easier, right? Those two things go a lot, right? It's cheaper, it's easier, and it's more widely available.
Everything can be measured via EIMS. It just goes in there and fragments. But for chemical ionization mass spec, it's more difficult. In order for it to be measured, it has to have a reaction that transfers that ion from the original ion to the analyte you're looking at. Now, chemical ionization mass spec can also be used for things that are very short-lived. So for instance, here's an example of something measuring OH. Remember, OH lasts for a second in the atmosphere. It can be measured by reacting with SO2 to form H2SO4, and then that H2SO4 get measured with these SIMS. And so doing this just allows you to measure a lot more things than you can with the electron impact. But it's very specific. It has to do that reaction.
This, by the way, is a really complex thing where they have a quadruple, they have an ion trap on this one, right? This is a really advanced. The other thing that's hard about SIMS and why it's more expensive and harder is you really have to calibrate it, okay? Because you're not measuring just how OH is in the instrument. You have to say, oh, how OH reacts with the SO2, and then how this reacts with the instrument, right? So you have. Okay. All right. So, oh, this is just another example, right? You can even, with mass spec,
you can measure isotopes. So remember what an isotope is isotope is when you have the same element or same compound, but with different masses. And that comes about because you can have carbon 12 or carbon 13. Carbon 13 has an extra neutron. Okay? And so, for instance, this is something for CO2. You can have CO2, and that carbon could be carbon 12, 13, or 14. The majority is carbon 12, and what you can have is you can have carbon 12 and have it with...
If you have CO2, right? In addition, you have oxygen 16, and you have oxygen 17 and oxygen 18. Well, what can you do? You could have a carbon 12 and two oxygen 16s, and that would give you a CO2 with a mass of 44. Okay? This is the vast majority of the CO2 in the world. Okay, 98%. Or you could have carbon 13 with two oxygen 16s, or a carbon 12 and oxygen 17, oxygen 16. This will give you a mass of 45. You could have another variety where you have two, you could add up to a mass of 46. Okay? Each one of these has a smaller abundance, right? Most of it's CO2 44, smaller amount is 45, 46.
Now, why would you care about isotopes? You may be thinking that, okay, it's just CO2, CO2. But different isotopes of CO2 determine where that CO2 is coming from. So, for instance, when you burn fossil fuels, the fossil fuels will have carbon that is older, and therefore it will have lower amount of carbon 13. All right, so if you look at a type of the CO2 in the air, and you measure how much of it is 44 versus 45, 46, that can tell you the source of it. CO2 coming from fossil fuels, right, burning of fossil fuels, will have less of the 45 than CO2 coming, let's say, from my exhaled breath. So that was talking about mass spec, right? We have chemical ionization, electron impact, and then we talked about isotope ratio mass spec. Now, another way to measure things is through absorption. You've done this already with a UV-Vis or FTIR. So let's look at the solar spectrum.
At the very beginning, when talking about the solar spectrum, we said, hey, ozone absorbs this UV light. CO2, we get these chunks out of the solar spectrum because CO2 absorbs infrared.
It absorbs infrared light. Specifically, you can see that notch right around 2 microns.
You can take a cell, you can run air through that cell, and you can shine light on it. And by doing this, right, at different of either CO2 or ozone or something else there is. So ozone, you would shine light at 254 nanometers, whereas CO2, you could shine it at 2 or 4 microns.
All right, so that is it on gas phase measurements. We talked about GC. GC is good for long-lived species and for low sample frequency, right? 0.02 hertz, right? Remember, hertz is 1 over seconds, right? So 0.02 means you're measuring at less than 1 per second. Then we talked about mass spectrometry and absorption. these more limited species, but you can do real-time measurements, and that's because you can have high sample frequency in 1 hertz or even quicker.
We talk about high sampling frequency. We talk about frequency of measurement in hertz. Okay, so hertz is 1/seconds. So if you measure 1 sample every second, that would be 1 hertz. If you're trying to understand
something that happens over a short time period, like let's say you're trying to understand what happens if you're sampling a fire, you really want to have 1 hertz for that. All right, so it didn't pick up a lot of this discussion of aerosols, so I'm going to do my best. You probably noticed when I re-record, I end up talking less, so there may be some blank spots. All right, so first remember, why do we care about aerosols? These 3 reasons: visibility, aerosols affect climate change, and then health effects. And we can measure a lot of different things: composition, size, optical properties. And what we measure really depends on what we care about, right? So for health effects, we really care about the size because that tells us how deep it goes, and composition because there could be hazardous things on there. But for climate change, we really care about the optical properties. Now, for aerosols, we'll talk about real-time and delayed measurement. Real-time meaning you take that measurement and you get it right away. Delayed is you take that measurement and it takes a while to get back the data, right? Think about it, if you had a blood test and they took out blood, you're not going to get that result for a week. Whereas if you have one of those sensors that goes on your hand, you'll get you'll get it right away. So we're talking about the same thing with aerosols. All right, so the first way to do it, and this is a delayed measurement, is what's called filter sampling. So what you do is you flow air with basically a huge pump. That pump just pulls in the air at a certain flow rate. And between the outside air and the pump, you have a filter, and that filter just collects the aerosol on it. You can do this for a certain amount of time. For instance, regulatory agencies do it for 24 hours, or you could do it for longer or shorter. And what you can do is once you have that filter, you can do all kinds of measurement. You could measure the mass of the aerosol by basically weighing that filter, or you can do some sampling where you extract it and figure out the composition, or you can what my group has done from time to time is you extract it and then look at the health effects. All right, this is the beta attenuation or BAMS measurement. This is how regulatory agencies measure PM 2.4 or PM 10, right? The particulate mass for aerosols smaller than 2.5 micron or 10 micron. And so you can see on top the air flows in through that inlet, and then the air flows through that tape, and that tape is filter paper. And basically what happens is the aerosols get trapped on the filter paper, and then beta particles are shined across that filter, and by the way that it, here it is, so that beta reactor, by the way, beta particles are electrons, right? And basically, by how those electrons are detected tells us about the mass of the aerosol on there. And so you can do this, you can do it continuously. You notice that it has those rollers, so you can basically set it to collect for, let's say, a minute, and then detect the mass, or you could do it longer. It just collects, rolls to the next spot, and does that. All right, here we're talking about what are called cyclones. Cyclones allow us to basically uh, only sample a certain type of aerosol. Okay, so you have that inlet at the very top, what looks kind of like a hat on the top. And then about halfway down, you have this cyclone. That cyclone, what it does is air travels down it, and then the air has to go in a circle and then go down and out to the sample instruments at the bottom. And so, based on the flow rate through that cyclone, determines what size aerosol actually makes it through. And so, if you have higher flow through there, the particles have to be really small to make it through that complex route. If they're really big, they're going to hit the side of the wall. All right, so what we were talking about earlier was delayed measurements, right? You have a filter and you collect the sample, you measure it sometime later. Now let's talk about some real-time measurements with what's called an aerosol mass spectrometer, or AMS. So what happens is the air comes in through the side there, and basically you have a pump that basically gets rid of a lot of the air, gets rid of a lot of the particles. Only a few actually make it to where that red line is. And that's basically a laser that basically vaporizes those aerosols. So they turn into the gas phase. Then those, and it also turns them into ions. So then those ions kind of make a right turn and they go up and they enter up into the mass spectrometer region. And in that mass spectrometer region, because they're ions, you basically have a reflector on one side, which has the opposite or the same charge, and so they travel in one way, and then they go the other way, and then that's where you measure them at a detector. So AMS is really good at measuring the composition of aerosols, and you can do this in real time. This is a figure from a paper looking at aerosol mass spec measurements, AMS measurements, throughout the world. And so uh, in red dots are where they made a lot of measurements. You'll notice that it's heavily, a lot in Europe, a lot in the US, not as much in Asia or other places. Definitely not in India and China. Those are the two most populated areas in the world, countries in the world, but not a lot of data. So what they did was for each place, they basically looked at, okay, how much organics they have in green, how much ammonium in orange or yellow, how much sulfate in red, and how much nitrate in blue. And so what you can see is, on the right in Riverside, where we are, about 50% organics, a lot of nitrate, and, about the same amount sulfate. If you go to Pittsburgh, right, it's upper left-hand corner, there, sulfate is almost 50%. Organics is still big, but nitrate's very small. So in Riverside, and in Southern California, we have not a lot of nitrate because a lot of cars. We don't have a lot of sulfate because we don't use coal. Whereas in Pittsburgh, they are in a region with a lot of coal. Nitrate's not going to be as important. If you go to, let's see, someplace like Mexico City, you can see that organics dominate. That's probably because a lot of the vegetation, right? And you can see variability, but usually in most places, organics dominate. Okay. Now we're on to optical measurement. So understanding the interaction of aerosols with light. And so remember, we have aerosols, they can scatter, they can absorb light, and extinction is the sum of these two. A key driver for understanding the optical properties and climate change effects of aerosols is what's called the single scattering albedo, or SSA. So what's albedo? Albedo, if you're talking about like a surface of a location.
I first learned about what albedo was when I was, talking to someone about snow measurements, right? Albedo is how much of the sunlight gets reflected back. So if you're talking about snow, about 90% of the light gets reflected back, right? That's why if you go skiing, you have to have sunglasses on, right? Because you get all that sunlight coming back at you. Something like the ocean, it's going to be only about something like maybe 40% coming back. If you're thinking about asphalt, right, it may be 10%. So that's albedo when we talk about like land surface. Well, what's this when we talk about aerosols? In aerosols, single scattering albedo is what percentage of the light hitting there is scattered versus how much is absorbed in there. So single scattering albedo is scattering over extinction, or scattering over scattering plus absorption.
High SSA, these are things like sea salt and sulfate. These tend to cool the atmosphere. Meanwhile, low SSA, like what you get from soot or other dark aerosols, these warm the atmosphere. And so understanding the SSA of aerosols tells us what their climate change effects are.
All right, so we care a lot about the optical properties. Okay? We care a lot, and we'll get to this in a second, also because when you have a satellite, we put up a satellite for $1 billion, right? All it's really measuring is light. Okay, so light coming into that satellite. So when we talk about pollution, we're really talking about the optical properties of pollution. All right, another thing that we won't get into because it's kind of annoying, and so is measuring the water uptake of aerosols. This is the number one uncertainty in a lot of climate change things. Right? There's actually I just got a note for a podcast I listened to, and they're talking, NASA's new satellite's going to determine the number one uncertainty in climate change, right? I'll listen to it and I'll tell you more next time. All right. Okay,
So we just talked about the optical properties, whether aerosol will scatter or absorb, and their SSA. Now, this is important because remote sensors like satellites or remote sensors on the ground, they measure optical properties. But a key thing is that if you have a satellite, so I have a satellite there, and the map on the ground is of the Baltimore, Maryland region and DC region, that satellite isn't just measuring the air quality at the surface. What it's doing is it's measuring all the aerosol or all the pollution between the satellite and the ground. Okay? Now for aerosols, that column, the entire column of aerosol is what's called the aerosol optical depth, or AOD. And so what we're doing is that's what our satellites are measuring, but what we really care about is what's at the ground. All right, so what are we talking about when we talk about remote sensing? Remote sensing is acquiring atmospheric data, right? So information on where pollution is, or wind, or temperature, or something like that, without physically contacting it, right? So not having a sensor to measure it, but to get information on everything above or everything below. So typically we talk about satellites in this regard. They are traveling way above us and they measure aerosol below, but you can also have remote sensing from the ground looking up or from a plane looking down.
satellites can only use light. Okay, they're not going to have a pump. They're not in all they're measuring. I have here, this is satellites, this is from a plane, this is from ground site. You can see that laser going in. Okay. So I talked about lasers. That could be a type of light. What other light do you think that satellites use? Infrared, right? What are the light source, I should say? So some satellites have lasers, right? There's a ground site that has a laser. What other light source do you think they use? What's the most important light source in the entire world? The sun, right? A lot of them use the sun. Okay. All right, so we can have some satellites that are what we call passive. That is, there's sunlight hitting the Earth and then going back to that satellite. That's the vast majority of satellites. A very small percentage are what we call active satellites. These actually use a laser to shine.
All right, so this is a illustration of NASA satellites. It's not all of them. It's a little out of date, but they're satellites. Most of them are in what we call low Earth orbit, which is about 705 kilometers high. That's the same altitude as the International Space Station. At that altitude, they're going around the Earth. You can see they're going around the Earth fast. They make 14 orbits per day, right? So they're traveling around it per day. And as the Earth rotates, they're making different passes over the Earth at different locations. Now, one thing is that even though they're getting global coverage, they are not getting temporal data. They're getting not a lot of information on how pollution varies throughout the day, right? In most places, they only pass over once per day. And so you can see all these satellites. One group I'm going to point out are a group that are going to come from the bottom in just a little bit. Oops, sorry, it just refreshed. So this group, OCO2 and the others, notice how there are like 5 satellites that go in a concerted, what they call satellite train. The reason for that is they want to be able to compare all their different measurements and kind of put them together to get information on the Earth. Now, some of these will measure things like pollution, but some are measuring the soil moisture or ocean color or ocean temperature, stuff like that. Over on the bottom left, this is a map of what they might give you as far as data for the United States. So this is a map you might get of pollution for a specific day with a satellite called MODIS. So this is for July 21st, 2011 over the United States. Red is high AOD, so a lot of aerosols. Blue is low AOD. And remember, this is the entire column, not necessarily what's at the ground, the entire column. So where do we see pollution? Well, the highest reds we can see over the North Carolina, South Carolina region. We see those reds, but really along the eastern seaboard, we're seeing a lot. You can see some really high red if you look kind of east of the Massachusetts area in New York. But you'll see that cloud kind of intersects it. So one of the drawbacks of this and the arch rival to satellites are clouds. The clouds basically make it so that they can't get it because the clouds stop the light from penetrating. So you can see places with clouds don't see it. You also see some places like in, well, Southern California up through Nevada where it doesn't look like there are clouds, but there's no data either. It's not blue or red or anything. Well, that's where there are just enough clouds to cause an issue. Here I'm just talking about a group of satellites called the A train. This is a satellite train where they kind of go in motion together, right? And they go in motion, and they're called the A train because they pass over locations on the Earth in the afternoon, so afternoon train. And so you have different measurements. You have some that measure aerosols, gases, clouds, water cycles, sea surface temperature, soil moisture. And you just have all these so you can put them together, right? If you understand the soil moisture, you may be able to say, hey, what effect does this have on emissions of different gases? So stuff like that, it's really valuable to have all these measurements together. Now, each one of these was put up at a different time, and each one costs a lot of money. So sometimes they die out, right? They're only up there for a certain point. And so they have to put more satellites into space to try and understand pollution on Earth. All right, so the satellites we talked about so far are in what's called low Earth orbit. Low Earth orbit means that they're at 700 kilometers high and they kind of move in relation to the Earth. So at one point they may be measuring over what's shown in that picture, over Alaska. Later they're measuring over the Atlantic Ocean. Future satellites are going to be in what is called geostationary Earth orbit. Geostationary Earth orbit is 36,000 kilometers high, way higher. And what's special about this is, in order to stay at that altitude, they have to go at 7,000 miles per hour. If they go faster than that, they'll go out into space. If they go slower than that, they'll crash into Earth. So the satellite has to have that momentum. Well, that is the same speed as the Earth rotates. And so if you have that satellite going around Earth at the same speed that the Earth rotates, that means it can basically be parked over one location on Earth. Okay? Now both are moving, blah, blah, blah. But relatively, it's just over one spot. So for instance, in this diagram, you see that satellite right over North America. And so what it can do is it can get you information on pollution throughout the day. All right, so this is just a comparison. Low Earth or current orbit, you can't quite see it, but that's basically that green area, or the blue area is the low Earth orbit. The future satellites will be in geostationary Earth orbit, which I think is the end of the green. And just for comparison, on the bottom, it's zoomed out, and so there's Earth, and all the way on right is the moon. Okay, so when they're talking about low Earth orbit, they're going to that blue area. Future satellites in geostationary Earth orbit are in that green area at the far ends. But to try to get to the moon, which is why we don't do it that often, or we haven't with humans in 50 years, is because it just takes a lot of effort to get out to the moon. So this is the first of one of those satellites in what's called geostationary Earth orbit. And this is, it has been launched already, and it is basically focused on North America. So as the Earth rotates, it's going around such that it can be always over Earth. And what it has is a swivel on it, so it can look at the East Coast, then to the West Coast, go back to the East Coast, and then the West Coast, and get you data throughout the day. Every hour you get data on pollution in North America, which is really cool. Different than the other satellites, which are getting you one snapshot of pollution per day. All right, now in a lab, in one of the labs, the next lab we're going to use is a satellite lab, and it's going to use Giovanni, which is a data resource to look at the data. Now, all the EPA and NASA data is publicly available. You've already used the EPA data. We're going to use NASA data in the future. Why is that the case? Well, it costs a lot of money to put those satellites into the air, and we're paying for it. So we want to make sure we get as much out of it as possible. Right? So we're paying for it, so we got to be able to see that data. All right, we're almost done. Next time we'll talk about airborne measurements. Airborne measurements is a way to basically be able to tie ground-based measurements into measurements throughout the troposphere and into the stratosphere to try to tie together ground-based measurements to satellite measurements.
All right. So we will get together on Thursday. I don't know who has done homework, who has not, but if you have not, remember that there is homework due tonight. Okay? Someone didn't sign in. Oh, there you go.
Hey, two questions. Oh, let me stop this.